Infinity is not like any other finite number. For example, we know that 5 minus 5 equals 0. 1005 minus 1005 equals 0, as well as 10 to the power of million minus 10 to the power of million equals 0. In general, no matter how large the number k is, if k is a finite number, then k minus k equals 0. We would like also to believe that infinity minus infinity equals 0, but this is generally false. In general, no matter how large the number k is, if it is finite number, then k over k equals 1. We like to believe that infinity over infinity equals 1, but this is generally false. The reason infinity is unlike any other finite number is that infinity is not fixed on the real line. For example, this number is a fixed number on the real line, and also this number. This number can be very large, but if it's finite, it has a very specific location on the real line. But what about x equals infinity? There's no specific location. If you want this to be infinity, what about this guy? It's even more infinity. And if you like this to be fixed somehow there, then this is not minus infinity because, maybe it's even more there. And obviously it's endless and it's not fixed. A fixed location on the real line makes comparison between two finite numbers really easy. For example, if you take those two numbers, why do we know that 10,000 is greater than the other one? It's because if you look at the location on the real line, you can see that 10,000 is to the right of negative 100,000. So it is larger. Definition: if a function f can be made arbitrarily large by choosing x close to c, but not c itself, from the right and left of c, we say that the limit of the function when x approaches c equals infinity. It looks like this. You can see that if we are approaching on the graph from the left and from the right to the value at x equals c, we are going up and up and up forever, which means that f can be made arbitrarily large. Here is the matching definition of limit being minus infinity. If a function f can be made arbitrarily small by choosing x close to c, but not c itself, from the right and the left of c, we say that the limit of fx when x approaches c is minus infinity. Here is an example for such a graph of a function that approaches negative infinity when x approaches c. Be careful. We extend the existence of limit to infinite limits. In this case, now you are not allowed to say that the limit of the function when x approaches 0 does not exist because this is an infinite limit. We are going now to treat infinity and minus infinity as if they were numbers, like finite numbers, even though they are not. In this case, the reason there is no limit is because 1, 2, 3 fails. 1, the right limit of the function at 0 is infinity. The left limit at 0 is negative infinity. And 3 fails because the right and the left limit are not the same. So we conclude that the limit does not exist But the reason for this is because 1, 2, 3 fails, again, not because it is infinite. Basic limits to infinity. For any constant k which is not 0, k over infinity is 0, because you are dividing finite number of items to infinity many pieces. We conclude then, and it makes sense, that the limit of kx when x approaches infinity equals 0. For any constant k which is positive, infinity over k, or k times infinity, is obviously huge. If you divide a huge number by a finite number, it's still huge. And obviously, if you multiply a finite number by a huge number, it's still huge. So we get here that limit of x over k when x approaches infinity is infinity, and also that the limit of k times x when x approaches infinity is infinity. Example, the limit of 2x when x approaches infinity is infinity. And here's the matching limits for any constant k which is negative. In this case, because k is negative and infinity is positive, you have to get negative infinity because you have plus and minus, and it's a product or a quotient. And we get the two following limits. Limit of x over k when x approaches infinity is negative infinity. And limit of k times x when x approaches infinity is now negative infinity as well. Example, the limit of negative 2x when x approaches infinity is negative infinity. And here are some basic to negative infinity. For any constant k which is not 0, we here have the same situation that if you divide a constant by a huge negative number, you still will get 0. And we conclude that the limit of k over x when x approaches negative infinity equals 0. For any positive constant, now in this case we will get negative infinity because it's the product of quotient of a positive and a negative. And we get two limits. The limits of x over k when x approaches negative infinity is negative infinity. And also the limit of k times x when x approaches to negative infinity is negative infinity. The truth is that there is not really much difference between over k and times k, because any constant number which is positive can be also written as 1 over another constant number. Example, limit of 2x when x approaches to negative infinity is negative infinity. And what happens when k is negative? Then we get here a product and quotient of two negative numbers, so we get plus infinity, and we get the following two limits, the limit of x over k and the limit of k times x when x approaches to negative infinity is just infinity. Example, limit when x approaches negative infinity of negative 2x is infinity. Be careful. All the properties of limits that we know are true only if the limit of fx and gx when x approaches c are finite. If one of these limits is infinite, then most of these properties are meaningless. To understand undetermined forms, we really like again to compare finite and infinite numbers. K minus K0 But infinity minus infinity, it can be anything. K over K is 1, but I just gave you an example in which you saw that infinity of infinity can be anything. In general, plus minus infinity over plus minus infinity or 0 over 0 can be anything. K to the power of 0 is 1. But plus minus infinity to the power of 0 can be anything, and also 0 to the power of infinity can be anything. You probably wonder how come 0, which is kind of a finite number. Yes, but you have to understand. 0 is the reciprocal of infinity. All those forms are called indeterminate forms. It can be any finite or infinite number.